Okay. Oh. Jordan, we should be live.
Live?
Live, yeah, of course. Live. Now we are live on YouTube.
Fantastic. Good evening, everybody.
Okay. Yeah, I'm so sorry for some technical connection issue. But hi to everyone. So my name is Tanya, and you're on the Professor channel. I really hope that you hear us and can see us. So if not, just please write in the chat about it. Okay. So today we are talking about mathematics, and I have a fantastic guest, Jordan Ellenberg, who is professor of mathematics, and actually he's the author of the truly bestseller, How Not to Be Wrong, and actually the new bestseller, The Shape, but we will talk about it later. Okay, Jordan, first of all, I would like to say thank you for this opportunity to talk with you today. And yeah,
well, thank you for bringing me on.
yeah, and you should know that your book is very special for our community, because we started to read this book just at the beginning of the year, and then the war started, and we needed to stop it. But it was actually the reason to rejoin and to continue to read this book and finish all together. So it was like some point of strength. And today I have a lot of questions for you from our community. So I hope that you're ready, and I really hope that our viewers now on YouTube will have some questions too, and you can actually type to us, and I will ask Jordan about it. Okay, let's start. We have only 1 hour. So my question, to all mathematicians, I'm just curious, when did you decide to be a mathematician? How it was?
Well, if you've asked this to a lot of mathematicians, I'm sure you've gotten a lot of different answers. So for me, I was very interested in math from a very young age, like as long as I can remember, even when I was a small child. And I think, I always feel a little uncomfortable saying that, because I think there's a stereotype that mathematicians come in the womb, right? That sort of people are born knowing that they're super excited about mathematics and want to think about things mathematically. And I would say, as a grown-up mathematician who knows a lot of people, I know that that is not everybody's story, but it was actually my story. So
okay. So I know that your parents, they are statisticians, so it's
right.
Somehow connected to mathematics. So maybe it was some kind of influence of parents, or it's not the case.
Yeah, well, first of all, it's funny. My parents are very applied statisticians. My dad always likes to say that he proved his last theorem in his PhD thesis and never proved it again. So I mean, they're the kind of statisticians who work on applied topics. They work in medicine and clinical trials and things of that kind. So so my life as a pure mathematician is, of course, very different from what they do. Also, my mom got her PhD after, when I was a little kid. So actually, but before I was born, my mom was a high school math teacher. So we did have a lot of books and stuff in the house, a lot of math materials, because that's what my mom was doing at the time.
Okay, I see. Okay, so the next, I guess, a usual question about the story with your book. So what was the idea? How did you come up with the idea to write this book?
Well, that's a great question. So first of all, I should say I was always interested in math when I was a young child, but I was also interested in writing too, always. And so I did a lot of, I wrote a lot on my own. I did a lot of courses. And, after I was in college, I went to a graduate program in writing and wrote a novel. I thought maybe I'll become a novelist, and a literary person. And I just discovered I didn't like that life. I was unhappy all the time. It's very hard work. It's very, you're alone with yourself a lot. And so I went back and I went back to math. I went and got my PhD and went on. But I think, but so I always had this practice of writing in mind. And then over the years, I started doing journalism, writing short articles for newspapers and magazines on mathematical topics. And I guess, the time to write a book. I mean, I'll say this, if anybody out there is thinking about writing a book, I think sometimes people feel like, well, you've got to wait for the moment of inspiration to strike. I think that's really wrong. I think writing a book is too hard and too much work to do it because you're inspired. You know, you can wait your whole life for that much inspiration to come. I think it's often more just a matter of circumstance and opportunity. So in my case, you know, we have in American academia, we have a sabbatical system where every 7 years you have a year of release from teaching to work on like whatever big project you want to do. So when I had my first sabbatical, you know, I had originally thought, well, maybe we'll like move and live in some exotic place for a year and work with different people on research. But, you know, my kids were very small. It was like, it's quite challenging to like move the whole family. So, so I was staying there where, you know, where we live in Madison. And I guess I felt that I did want to do something. I did want to spend that year doing something really different from what I was otherwise doing. And so that was when I was like, well, maybe now's the time. Maybe now's the time you know, to write a book. And so that was, I mean, so it sort of seems funny to say, but that was why I did it, because circumstances created the opportunity and the time to do it.
And why this book? Why like not about I don't know, deep mathematics or something like that? So broad, how not to be wrong.
Well, that's a good question. So first of all, I want to push back, because actually I do think that book is about deep mathematics. And I think, you know, I make this in the beginning of the book, I make this little quadrant figure where I'm like, well, there's 4 kinds of mathematics, right? It can be simple or to explain, or it can be complicated to understand, and it can be shallow or it can be deep. And of course, you know, as a research mathematician, I spend much of my life in the zone of things that are very complicated and hopefully deep. I mean, I try to make it as deep as I can.
Definitely. I saw your papers.
But for a book of this kind, I think it's an opportunity to do what actually can be explained in English words and doesn't require a lot of background, but ideas which are quite deep. And that was one reason I was excited about writing a book. You know, I had written lots of articles in the past, but in a 1,000-word article for a magazine, there's lots of ideas that you simply can't really explore in a short space. It's not that the reader needs a lot of technical background or a lot of know-how or to know what all the Greek letters mean or something like that, but you do need the reader to commit to spend a certain amount of time and a certain amount of thought with you. And that you can only get in a book. You know, to make a brief digression, somebody once said to me, okay, I'm going to complicate this in 2 ways. One, I was just remembering, I saw like an interview with this like famous like fellow who stole all this people's money and with his crypto exchange, Sam Bankman-Fried, saying like, he doesn't read books. He feels that books are a waste of time. Somebody else told me, why do we still have books like when there's Twitter? Like if an idea is important, like if it's really important, like shouldn't it be able to fit in like the space of like a Twitter thread? Like why would you waste 300 pages writing a book? So that I think is like a degradation of intellectual life. So one reason I did it is because I truly believe that there's certain kinds of ideas that simply require spending some hours and spending some pages and stretching out. And I love Twitter, by the way. I tweet all the time. The viewers are welcome to go look at it. But there's certain kinds of things that you can do very effectively on social media, but not everything by any means. Yeah. Writing books is an opportunity to do those things where you go deep and you stretch out, and when there's a digression or a pathway, you follow it and then come back. And I think despite the fact that the book is a very, very old communication medium, I don't think we've come up with a better way to do that kind of work than in a book.
Yeah, but yeah.
Do you feel like it's still a book culture, or do you feel like Ukraine has like been social mediaized like the United States?
It's better not to ask me. Maybe our viewers, you can type because I like really like fan of the books of the like even like paper one, and to read deeply. I'm not a fast reader at all, so I guess like some deep stuff you can like get only by reading and this like huge amount. And I really appreciate the books where the author like lead the thinking. It's your book actually. You lead your like way of thinking from one way to another, and that's really fantastic. That's really cool.
Yeah, and I'm mimicking my own process, because the truth is, I think I know what is going to be in the book before I start. I mean, I have to submit to the publisher, here's an outline of here's what chapter are going to be in it, here's what I'm going to write about. But as I start to research and really prepare the writing of the book, I find new things, I get excited, I follow a pathway. And that's what you're seeing on the page. I mean, you're seeing me learning it. With this book, with the first book, I think I wrote an outline for them with like 15 chapters. And I think I wrote like 3 of them, and that was like 300 pages. And that like took me a year. So, I mean, I wrote the publishers and I was like, well, do you want me to write only 5 of the chapters I said I was going to write and send you a 500-page book on time? Or do you want me to write them all and send you a 1,500-page book like 5 years from now? And they were like, definitely just do that. So they were fine with the fact that I didn't do everything I said I was going to do, because I didn't understand like how much I was going to learn in the process of writing and how much more I was going to want to do just about each topic as it's spread out. I mean,
yeah, that's true. On Friday we had a really great conversation with Thomas Corman, Clifford Stein, and Ronald Rivest with our students. And Thomas said that when like the professor like offered him to write the book, he was like a graduate student and say, oh, okay, that's fantastic to write the book. And he said that that's exactly the reason why I had like spent 8 years for a PhD because I wrote the book. So it's a huge work. I just can't imagine, because I have never write any of them. But still, I'm always wondering about your book, How Not to Be Wrong. So use mathematical reasoning, okay, let's say, and Kahneman. So Thinking Fast and Slow, where he, like Daniel Kahneman, he said that, and make a lot of researchers on even mathematicians, that usually you don't use in real situation all that you know, for example, from probability and etc. So I'm wondering, is it really possible to use it in a real situation? All like stuff that you like wrote.
Sure. Well, first of all, I very carefully didn't call it How Never to Be Wrong.
Okay. You know that in Ukrainian translation, we say like how never be wrong.
Really?
Yes. If you see, як ніколи, it's never. How never be. Yeah.
I'm gonna get sued for false advertising. I never meant to make that promise. That's too strong.
But maybe that's why you have so huge popularity of your book in Ukraine. So you never know.
People are very disappointed that they bought it, and they were still sometimes wrong about it. I mean, no, it's a very interesting question, especially, and it ties in with a lot of other stuff we're going to talk about, because what Daniel Kahneman writes about is, he's a psychologist, and he's writing about the human mind and human psychology, the way humans are. We are all human beings, even when we're doing math, even when we're doing the most formal kinds of mathematics. We're still human beings, and we're affected by our passions, we're affected by our personal relationships, we're affected by even the question of like what math we're interested in doing is a very human question. It's not a formal question that you can determine by logic alone, like what to be interested in. So when you say, I'm just based on my own knowledge of Kahneman's work. I don't think he would say that aspect of our mind can't affect our decision making. I just think he would say our decision making is always going to be much more than that. And I agree. I mean, I think the metaphor I use in the book is kind of like an exoskeleton, like a superhero wears. And now, actually, something that didn't really exist when I was writing, what I might use now is, do you ever ride an e-bike?
No.
These electric boosted bikes, they're very popular here.
Oh, okay. Yeah. Okay. Got it.
And what's cool about them is they're
Yeah.
built in such a way that, yes, you have more power and you can go up a hill much
Yeah.
more easily, but you feel like it's you, right?
Yeah.
It's your
Yeah,
foot
that's
pushing
true.
and you get a
That's
boost.
true.
It
Yeah.
doesn't feel like you're riding a car or a motorcycle where you feel like the machine is doing the work. And so I think math is like us. It's still the human being with our human interests who's driving, but I do feel like we can do stuff better than we do, and maybe be wrong in less damaging ways, or notice that we're wrong more quickly, be more reflective, be more attentive. I do think, I do think, let me put it this way. I think Kahneman is sort of writing more about these moments, these very fast decisions we make just in our everyday life as we walk down the street.
Yeah, that's true. That's true. More
And
about automatic.
And I'm writing both about that part of life, but also the part of life where, you're the mayor of a city and you're deciding things about where the buses are going to run and like where the train tracks should go, right? And there, I think that's slow thinking, right? Very slow, because you have to get it past.
Yeah, you're right.
I think in those areas too, we make some decisions quickly and we make some more reflectively, but we're never.
Yeah.
I think with this discourse, we're going to talk about it, about what's the relationship between. I just came from a wonderful conference that I helped organize about machine-assisted proofs, about math and machines, like to what extent, what parts of the mathematical program can computers help us do? And it's a very interesting topic, but one thing that's very clear is that mathematics is not just computation, right? It's not a purely formal enterprise. And so what I would never say, and I think sometimes people maybe who are worried that I will say is, oh, are you saying you should sort of junk human intuition, you should junk human spirit and replace it with mathematical calculation? No way, that's not the goal. The goal is for math to make us stronger at being humans.
Yeah. That's great. Actually, we have a very nice question from the chat. Can I
let's
read
do
it? Yeah. So the question is, some scientists told me that smart people don't read books, they write them. I disagree with this, but what do you think about this idea? Can it be true, at least at some extent?
I think the book that somebody would write who never read books would be an absolute disaster. Come on. They could, I guess.
Okay.
I thought you were going to say, a sort of another thing people say, which is just as bad, but in a different direction, is, oh, smart people don't read books. They have books written about them. That would be another way to think about it.
It could be. That's great. Okay.
Look, I don't even, to be honest with you, I don't even love the phrase smart people in the first place, because I think there's a huge wide range of intellectual virtue. So even though I'm a reader and I love reading books and I love the feeling of stretching out, I actually would never say that somebody who doesn't read books couldn't be smart. I think there's different intellectual virtues. And actually, I would say, even though I like to read a book, which takes 10 hours or something. Even within research mathematics, there's people whose ability to focus attention I envy so much. It's incredible, because in math, our time scale is not 10 hours, right? There's people I know who are I've been thinking about this problem for 25 years. That's our time scale.
Yes.
And I tend to not do that as a researcher. I tend to switch topics a lot. I sort of get fascinated with one thing and I jump from topic to topic. And that works great for me. That's my temperament. But there's certain kinds of depths of understanding that the people who really have it are the people who are I am going to study one thing and reflect upon it very deeply for 25 years of my life. That's an incredible commitment. And the world needs people who have that level of focus and sustained attention. But somebody who's not even willing to read a whole book is obviously not going to do that.
Okay, Jordan, prove by an example. Could you suggest some fresh book to read to our viewers?
Oh, wow.
Maybe not fresh, maybe like one of the last that you read and it was great.
I've got one that I really like that I just read, and it's not even out yet, but it's going to come out.
Okay.
Which is a book called The Autumn Ghost by Hannah Wunsch. And I really like it. It's about polio. It's about it's set mostly in the 1940s. A lot of it is in Denmark. And I thought it was a really, really wonderful portrait of how science gets done in reality. Like this question of like, how is scientific knowledge formed? And sometimes in class, it's taught in a very linear way. Like I would say, if you learn something about polio in school, right, you'll learn like, okay, there was this disease, it was bad, kids got paralyzed, there was the idea of vaccines that was older, that it was possible to expose people, and then so somebody developed a polio vaccine, and then polio was fixed. Well, the story is a lot more complicated than that, and it involves lots of scientists, like at various points, truly thinking they had polio's number and like understood what was going on, and their understanding was not correct, and like things went back and forth. There was arguments. I mean, I think she really helps us understand how messy scientific progress really is and how it's not linear. It involves a lot of improvisation. I think, with everything that's just happened with COVID, I think lots of people became very angry and said, like, why don't the scientists just figure this out? And I think it's because people have this very misleading idea of how scientific knowledge is actually generated. We don't, they say, I don't know if they have this saying in Ukrainian, but they say, you never want to see the sausage being made. It's delicious when you eat it, but you don't want to see.
Yeah.
But it's important, right? I think it's better if you see the sausage getting made. And that's what this book offers. So The Autumn Ghost, Hannah Wunsch, about polio, coming out in a month or two in English. I thought that was great.
Thank you so much. You can it's really funny because now I'm studying on MIT course on statistics, and they use the case of polio just to investigate and all this stuff about vaccination and consent and blah blah blah. So actually, it's
and how not to be wrong. I mean, I learned a lot about the case of tobacco and how, I think modern people look back and are like, how, why didn't the government regulate tobacco sooner? Like, it must have been because, the companies really conspired to keep the knowledge that tobacco was bad for you from being known. And there is some of that. That's not exactly false, but it's also true that I think there was a long period of time where it was like legitimately controversial for actual good scientific reasons, before more experiments were done, that people had the idea that tobacco might be really bad for you. But I think it was a messy, complicated process by which we were able to arrive at actually understanding just how poisonous tobacco was.
I guess we should teach it in school, at least how scientific process began. We have a new, a lot of new questions to you. Are you ready?
Yeah, I'm super happy. There's lots coming in the chat. Let's see. Yeah.
Okay. Are math results discovered or invented? In his last interview, Nash said that for him, a result like a theorem is proved when correctly formulated. What is your view on this matter? So, discovered or invented?
I always like to say they're discovered, but the way we discover them is by inventing them.
It's not honest.
No, I mean, this is of course that answer is, I'm kind of serious, but it's kind of a joke at the same time. I mean, the other joke that is probably more true to mathematical practice is that people say we all would say invented on the weekends, but discovered on the weekdays, by which I mean that when you're actually working on mathematics, of course you feel that the things that you're studying are actually there to be found. I think it would be impossible to think about them if you were constantly doubting their actual existence.
Yeah.
And then maybe on the weekend, when you're not working and you're just being a philosopher, you can be like, well, perhaps they're creations of the mind, perhaps they're not really there. But then Monday rolls around and you open your notebook and you're like, oh, of course they're there. They're like right there. I'm thinking about them and experiencing them and perceiving them.
That's great. I've never heard about this, like, division by weekend. Okay. So the next one, it's not easier. So the next one about how machine learning influence current mathematics, if it is actually in which way. And I guess here we can talk about ChatGPT too.
Yeah, no, it's great, and I'm an optimist about this stuff. I mean, as I said, I just went to a whole workshop where we talked about really two different streams in the relationship between computers and mathematics. One is formalization. So one is the question of, can we write our mathematical work down in a way that a computer can read and a computer can check? You know, we already know how to do that for basic computations, but the question is, can we develop a good language in which we can write proofs of theorems that a computer can read? And then the parallel question is, what can machine learning do? And I think already it's just starting, but there's really very interesting work where we're saying, how can machine learning help in the process of what we would call hypothesis generation? Like, we're very good at proving things, but how do we know what to try to prove? So just as I think I tend to think of it as, just as physicists are very happy when there's a device that allows them to do experiments that they couldn't do before, with more experiments, they're more able to sort of generate good theories. I think the machines help us do good experiments in mathematics. They help us find regularities that we can then try to explain with theory. And there's some wonderful examples of that by pure mathematicians like Mark Lackenby and Jordy Williamson, who have worked with the folks at DeepMind, which is part of Alphabet, using their very powerful computational tools to sort of as kind of collaborators. So maybe, was that too vague? Should I sort of spell that out a little bit more? Like, I'll give an example of a wonderful talk I saw at this conference by Adam Wagner, who's a professor here in the US, about how, people study a branch of mathematics called graph theory. And they have a question. They're like, is it possible that every graph satisfies the following property? And they investigate it to some extent, talk about why it might be true, try to prove it, maybe can, maybe can't. What machine learning allows us to do is to be like, to very effectively search for counterexamples, to very effectively say like, I think this might be true of all graphs. But if I were, of course, when you think that something might be true, you try to put pressure on it and say, well, what if it's not true for all graphs? What kind of graphs would this statement be false for? But there's lots of graphs, right? A human can't think about them all at once. A machine is very good at searching a space, a large space that might be too big for a human to hold in their head all at once. And even better than that, not just searching it by looking at every single thing, because to be honest, these spaces we study are so big, they're too big for computers too. But searching the space intelligently. And if that sounds a little bit familiar, it's because that's exactly how computers became good at games like chess and Go. Right? A computer still doesn't know every single possible position in chess or Go. That's still too big, but they're very good at sort of developing good strategies for sort of searching the space and finding good directions to go. And so in the same way, I think that's a very promising new tool to help mathematicians in our work. Now, you may notice that what I'm not saying is, oh, when are computers going to replace mathematicians in like creativity, having the ideas? We don't really know, but at the moment, I guess that's not the way I'm seeing it going. I'm seeing this not being a huge discontinuity, but rather affecting us the way new technology has always affected us by like making us stronger or making us better able to do the things we want to do, but with the human being still in the driver's seat.
And okay, and what about children, for example, or students who can overuse it? I mean, use ChatGPT not like the best direction, not for research or for finding other examples, but just to solve. And I don't know, just to write the problem, give the solution for a teacher, and that's all.
Well, here's the funny thing. Like, I mean, it kind of, people are like, well, they see ChatGPT and they're like, well, what if this gave students, what if students had an easily accessible computer tool that would like basically do their math homework for them? Well, I got news for you, that they already have that. Like, that already exists. Like, most questions that are asked to students, if they need to do an integral in calculus class, I promise there are symbolic integral calculators everywhere on the web that will not only tell you the answer, but like list all the steps. That already exists. And we've made our peace with it. And I think a student with good conscience, look, I hate to like out him on live YouTube, but like my son uses that, but he uses it to check his answer. You know what I mean? A student with good conscience will like do the problem, and then they'll be like, okay, is my answer, before I turn it in, like, let me now check it and see if I got it right. And if I didn't, let me see what I went wrong. And when you think it that way, you're like, oh wait, that's actually good for education. So I want to I want to give the positive case. I feel like if we're like, what are we going to do in a world where kids could have the computer do their homework for them in math? That already exists, so I'm not so worried about that. But let me put the other side. I think, you know, a large language model labeled assistant, where the student has access to a chatbot, they're just doing they're like, okay, like I'm looking at my notes from class, I didn't understand this, can you explain this point? And the chatbot just says something, right? I mean, that I think could be very useful, like having a LLM enabled assistant at your side, like while you're doing the work. You know, anybody who's taught a large class knows that it would be great if we were there to answer every question for every student at every time of the day, but that's not feasible. And so I guess I have an optimistic vision that I think there's ways in which this will aid education. Look, in the same way that, I'll give you another example since we're on YouTube, when there started to be really good YouTube videos, you know, about various mathematical topics, I think people were like, well, how is this going to affect education? Are kids going to like not go to class? Like, no, they still do go to class. And maybe they watch that YouTube video also. I feel like, I always like to believe that it's going to add rather than subtract from education. But that's also because, you know, I mean, I teach in a college. I've taught in a college for a long time. It hasn't made me cynical. Like, I look at those kids who I see every year and I feel like, on the whole, they'd rather learn than not learn. I think that's true of today's generation of college kids, just like it was true when I was in college.
Okay, so maybe like a continuation of this. In Ukraine, we have such educational systems that almost everything in school, it is based really on some rules, formulas, just use this theorem and do this, and etc., etc. And I guess that's my opinion, that we don't have a lot of room for questioning. Discussion, like, not just say that, okay, don't divide by 0, but discuss why we can't divide by 0, because even I don't know what will happen and how to define it. So should we change it, especially with such tools like ChatGPT, Wolfram Alpha, and other solutions that we have, and speak more about like maybe some interesting like edge cases, not about only computations and the rules, or it's not possible?
I mean, it's not easy, but that doesn't mean it's not possible. I mean, like, nothing about teaching math is easy. I mean, so one thing, I feel like a lot of times people feel like I have the magic bullet and we're going to make teaching math easy or simple. That I don't think is possible, because I think math itself is not easy or simple. Like, math is quite difficult, and like, the things that, I mean, there are things we teach rather small children, which are conceptual advances that it took these like incredible minds like many years to sort of work out and understand, and they were the subject of much argument. I mean, I always say, what we do with like 10-year-olds when we teach them that a fraction is a number, that's an incredible conceptual advance, right?
Yeah.
Because up until that moment, and in fact, for probably 1,000 years of mathematics, a number was the answer to a question, how many? And then suddenly we're like, okay, 5/3 is a number now. That's certainly not the answer to a how many question. It's like a different kind of question. And the fact that you can manipulate a fraction and add it and multiply it and subtract it just like you can with ordinary whole numbers, that's incredible, actually. And then we're like, why is that hard for students to get? It's hard for students to get because it is hard. All right, I got a little other, but in terms of how formulaic we should be, it is an interesting question because I don't actually think, and this is a conversation we've been having ever since the calculator was invented, like, is it still a worthwhile skill for students to be able to reckon and do a certain amount of computation mentally, and swiftly? And I would say yes. I think it's actually quite hard to sort of I think it's hard to understand deeper concepts without a certain amount of just like muscle memory and fluency and ability to do those computations. I do think it's a bit of a shame if our math class is just that. I think it becomes, look, this is a subject, and I don't know how it plays out in Ukraine. In the United States, it's very politically hot. It's something which I think people instantly jump to conclusions and have very strong feelings about, which I think are typically much hotter than they need to be given what's actually being discussed. And so, you'll have the governor of a state saying like, well, in my state, we're never going to, we're not going to teach that there's like different solutions to a problem. And I'm like, why are you getting so upset about this? Like, there are different ways to do a problem in math. It's not like an attack on your religion or your people or something like that. But I think people tend to get very emotional about these issues in a way that's maybe not necessary. That said, right, I have one more thing to say about this. It's easy to say, well, we should teach a more conceptual curriculum where we do say like, well, why can't you divide by 0? Like, what would be wrong with doing that? Like, what would, but you have to make sure that teachers are ready for that. And I think sometimes what happens is somebody like me, right? Somebody like some person in a university or some person who's on a big blue ribbon commission or something will say like, well, we're going to make this ambitious, more conceptual math curriculum so our students are, ready for the 21st century or the 22nd century or whatever. Like, our students are going to be so far ahead. And then this is just like handed to teachers who have been teaching for a long time and are very good at doing it the way they've been doing it with very little support or preparation. And that's not going to work. Right? You can't do this by decree.
Yeah, you're right. Oh, we have a lot of questions in the chat. Okay.
Oh my God. I'm sorry. Are my answers too long? See, I talk like I write. I sort of get excited about something and then I go on.
No. It's really so interesting. And the questions are really deep. So, okay. So let's read the next one. There is a popular belief that gifted people with natural talents in some fields have perceptual biases, being sensitive to peculiar aspects, like musicians are noticing rhythm and tones, and artists pay attention to colors and scenes. Are there any mathematicians' perception biases? What falls into your eye more than others people?
Oh, that's a good question. And you could ask that about writers too, by the way.
Yeah.
Well, here's what's interesting. I think there's a bit of a stereotype, and I think people often even sort of do psychological studies to sort of see if this is like correlated with mathematical interest and skills of like, what's called spatial reasoning. You know, they give little kids tests like, okay, here's a picture of a thing from 2 angles. Which of the following could be a picture of the same thing from a 3rd angle or something like that? Like, can you mentally rotate things and visualize things in your mind? And one thing I find interesting about that is I cannot do that stuff at all. Like, I'm incredibly bad.
I don't believe.
Like if I'm inside my house and you point to a wall, like I can't really figure out what's outside that wall. I would have to like go outside and look. Like I can't sort of like reason my way to understanding unless I can look out the window, like what direction that would be. So I guess what I would say is, in my life in mathematics, I've come to feel that the way mathematicians are as people, like what their interests are, what their temperaments are, what their perceptual biases may be, has pretty much the same range as all people. I mean, what we have in common is that we all really like mathematics, but apart from that, we're quite different from each other. And I wouldn't say there's really any commonality except that we all like math.
That's interesting. Actually, I in some day I had a discussion with another mathematician, and he told me that it was pointed that like the most prominent, I don't know, like nice mathematicians, they always, when they thought about something really abstract, they always do something with hands, like show something. So
no, that's very common. In fact, I have a colleague here at Wisconsin who's a wonderful psychologist. She's a developmental psychologist, and she mostly works with kids, but like literally she has many papers about exactly this, what they call embodied cognition, like how children do this as they're thinking about math. To what extent? And I think that psychologists do believe that's actually part of our reasoning. It doesn't all take place inside the skull. Like we use our, another thing is that, I mean, not everybody, but we do walk in circles a lot. We pace. I mean, I think that's, at least for me, that's quite helpful for thinking mathematically, to like walk in a small circle.
Yeah. Okay. Now, the next question: wrong proofs. What is the value of them? Can we say that road to frontier of knowledge is longer with every generation?
Oh, long proofs. I thought you said wrong proofs. I was
wrong. First part is wrong proof, so it's not true, like not correct one. Like wrong proofs. Yeah. What is the value of them?
I mean, I prefer correct proofs, but it's certainly true that, like, I think in this way, I don't think math is different from any other creative field, in that you have to have the license to make mistakes. Like, you have to sort of have the mental permission to write something in your notebook or to say something in conversation or at the blackboard that's wrong, because otherwise you get, I don't know if it's okay to put it this way, constipated. I mean, you have to sort of be free enough to like let ideas come out, and they're not always going to be right the first time. I mean, I forgot what famous writer said this, but you write to find out what you think. You don't figure out what you think and then write it.
Yeah.
So I think sort of like feeling free to kind of make mistakes. Now, ideally, obviously, you sort of spew out lots of stuff and you're talking to other people and your mistakes get corrected, and sort of together you sort of like hammer out a path towards correctness. It is true. Like, I'll just cop to this. Like, I have written and posted like a proof that turned out to be wrong. Like, I gave many seminars about it. I mean, that's not great. It's not a very nice feeling. I felt I owed the community an apology. But I also felt like it's not the end of the world, and our community does have a pretty good ability to fix its own mistakes. Like, even if that process, as I was saying with polio, like maybe it's a little bit messier than we portray it, I think it works pretty well. And I think, by the way, it speaks to the very first question that somebody asked in the chat about, whether mathematical things are discovered or invented. I guess on some level, I have a feeling about the fact that our mistakes we tend to find our way towards correctness, and we tend to fix our mistakes. It sort of has to do with the fact that I do think in the end, the things we study in mathematics are real things. Yeah, I'll be honest. That's basically what I believe. I think they are real things. And that's why we tend to sort of move towards correctness, because we're not just playing a empty formal game.
I have a very interesting story about the discussion with my scientific advisor. Actually, in some moment in the past, I found the paper that was wrong, actually. So the proof was not correct. And then I came to my scientific advisor and said, okay, how it's possible, why it is published? There's something weird, and that's not good. I was young, and he said me, okay, but it's great paper. And I said, why it's great paper? It's wrong. Because it gave the opportunity me, like my scientific, to find the way how to prove it correctly. So this paper gave me an idea how to do it. And the next paper was like a continuation, and I proved this very nice theorem, because if I did not find this like wrong paper, I will not come in some idea. So it was in that moment, oh my God, really, it can work in that way. Like when you use brainstorm, maybe some bad ideas, bad proofs, like wrong proofs, can lead you in some fantastic results.
Right, because they usually have good ideas in them. And I think our intuition for when's an idea a good idea is probably better than our ability to be absolutely sure that our proofs are correct. Like if the person wrote that paper, they probably thought there were good ideas in it, and they were probably right about that.
Yeah. And the second part of this question, can we say that the road to frontier of knowledge is longer with every generation, that we stay on the like shoulders of giants?
That is a fascinating question. And it would be one sort of very sad end state for mathematics would be if it just became so hard to get up to the frontiers that people stopped doing it because nobody wanted to like be a student until they were 35 or 40 years old just to be able to interact with new mathematics. I guess I don't see that happening, because I think on the one hand, we keep on pushing the frontiers of knowledge outwards. On the other hand, I think we also sort of start to understand the more basic stuff better, and what was once considered very difficult and theoretical and only for grad students like becomes part of the undergraduate curriculum. And eventually, I mean, think about the fact that calculus is now like a normal high school class in the United States. Is it in Ukraine too, I'm guessing, calculus?
Yes.
Yeah. And it wasn't always, right? I mean, you know, to go back to the Soviet Union, right? Pre-Sputnik, calculus was not a normal high school class in America. And then all of a sudden it was like, we have to beat the Soviets by having calculus in every high school class, because we can't let the Soviet kids like be 1 year ahead in math. American kids. I mean,
it's always was the competition, I guess.
So I guess here's my optimistic take, which I think is not unreasonable, that like, yes, the frontiers get farther, but also our understanding of stuff leading up to the frontiers gets better. Our ability to explain it becomes better. And so kids can get there faster.
It's interesting. It's actually believed in that mathematics is actually for young scientists. I mean, if you don't do something really clever or fascinating in mathematics, like before, let's say 35, you don't have any chance to make something really distinct. What do you think about it? It's the science for young people or not?
Well, I think all my best work has been after age 35. So it's most people who consider my best theorems are all from after that. So
okay.
I think what I did before that was okay, but I mean, it's, no, I mean, I think it's complicated. I think, I think there's a certain kind of stamina that it's harder to have when you're older. I mean, I think I very rarely anymore go on what my wife likes to call a math frenzy, where I'll just like go for like 12 hours. Like I don't, but on the other hand, I also often spent 12 hours running down a path, which now I would recognize after 2 minutes was like not a worthwhile path. It wasn't going to work. So I think as you get older, on the one hand, you have less stamina. On the other hand, you have more perspective and a sort of better ability to sort of understand which paths are promising.
Oh my God! Well, this next question from the chat. When you tell about history of some math result, you usually have choice of telling refined proof or telling about how people try, failed, and so on. What is more appropriate and for what situation?
Okay, so for the kind of stuff that I write, absolutely the second is the right way to do it, telling about people's struggles and failures. And the reason for that is that, if I think of the books I write as being related to my teaching, I think one of the biggest challenges as a teacher of mathematics is, I would say quite simply, a challenge of empathy. You have to imagine yourself into the state of mind of not understanding something that I, in fact, do understand very well, right? And that's a challenge. You're sort of imagining yourself being different than you are. That's hard. But if you don't do that, it's very hard to teach, right? If you imagine the student in front of you already understanding it, then how can you teach? You can't. And so I think when I write about math, I have found that a very useful, it's a trick, but it works. Like a very good way to put yourself in contact with the state of mind of not understanding something is like literally to go back in history to people who were like very accomplished and very smart and very wonderful people with lots of virtues, but who did not understand that thing, and see, okay, what we can tell what their minds were like because we can read what they were writing. And we can see their struggles like on the page. And I've found that to be like a very useful way of conveying the concepts, especially because, I think for many readers, the very basic fact about math is that every single thing in math was invented by human beings to solve some problem that people were having. And I think we can lose sight of that when we give the refined presentation, which, by the way, I think is very appropriate for school. But I do think it sort of hides the mess a little bit. And in the books, I think it's a really great opportunity to sort of like to present a little bit about that mess and kind of give readers a character who, a historical character who's like struggling to understand this material. That gives the reader somebody who they can identify with. And that's not really present in the classroom, right? The student doesn't have that person because I obviously am not struggling to understand what I'm teaching.
And we have a lot of some like facts. I don't know, just okay, we need to solve some quadratic equation. What is this is discriminant and blah blah blah. And the person sit and okay, why do I need this? What is this? And I mean, a lot of children just don't know which problems were behind this. We have some really clean.
I would never deny, by the way, I feel like we've talked a lot about this need to sort of talk about the concepts and the meaning and the historical origin of a problem. But I will be honest and say that it's also the case that there's something quite satisfying about the pure computation, about the fact that you can use the quadratic formula and then you get a value, and if you plug it back into the equation, you're like, dang, it's actually 0. Like that actually works. It's like Lego, right? Like Lego is maybe not necessarily creative, especially if you're following like a plan, like, okay, it says exactly how to build this spaceship and you do it, but it is very satisfying. Like there's a reason like doing it. It's awesome the way like all fits together exactly the way you were told it was going to fit together. And I don't think that's like I think that is intellectual too. And that feeling of successfully clicking together, that's also an incredibly important part of what it is to think mathematically. And we should go for that too, and not denigrate it as being merely formulaic.
Okay, so let's talk about pure mathematics and some kind of reality. So I have two questions for this. So first question about your quotes that you blame word problems. They give a badly wrong impression of the relation between mathematics and reality. So the first question, so actually, is it possible to create such problems that will be real world problems? So for teaching, so and maybe don't create it and just give only pure mathematics and that's all.
I think both are important, and I think that's traditional, and I think it's a tradition that's pretty much correct to kind of mix purely symbolic problems and word problems. I just think the word problems, should actually be word problems and shouldn't just be like a symbolic problem, solve 3x plus 7 equals 8, just translated in some. Okay, I'll give you an example. I was helping my son study for a calculus exam, and there was a sample problem where it was like, well, okay, there's like fish in a lake, and the population of fish is modeled by the differential equation that the derivative of the number of fish is like, hyperbolic sine of the number of fish plus this exponential or something like that. And I'm just like, what the hell kind of fish could that possibly be? Like, that makes no sense. If you want to just give them a differential equation to solve, just give them the equation, but don't bring the fish into it. No fish in history knows what a hyperbolic sine function is or reproduces like according to that law. It's absolutely nonsensical. So I guess that's the kind of thing I object to, and it is very common. I think problems that are simply solve this differential equation should just say that. And if they're going to ask a question that sort of is supposed to give some sense of why differential equations are so incredibly important in science, then you got to use a realistic differential equation for that actual scientific situation. And if it happens to not be that hard of a differential equation, like so be it. But don't lie about fish.
Yeah. That's true. I guess sometimes we like overplay with some word context for mathematics. Okay, so the second question for this is like more complex, like not the easier one. It's about pure mathematics and reality, and about the application. Actually, I had the discussion with my scientific advisor too, because when I just came for the first time to him, and he showed me a very nice problem in matrix analysis, and I heard very attentively, and then asked him, okay, what is the application of this problem? And he was like dumb. He don't talk with me at least for one day, and then give me a lecture that we are pure mathematicians and we don't need to care about any application, and etc. etc. But still, is it really like the case that scientists should care about some applications or do some pure mathematics and that's all?
I would say I'm going to say no to any question that has the phrase "should care," because I don't think there are sort of like moral considerations in like what we care about. I think people care about different things, and math is so we have a temperament that sort of governs what we care about, and I think math is like too hard to do stuff you don't really care about. So if somebody was like really fascinated by an area of pure mathematics that had no applications, whatever, and they woke up in the morning and they said like, well, I should care about more applied stuff, I should go make myself work on something that has more direct applications, guess what? That person is not going to do great work, because if they're not doing what they actually care about, it's just too hard. It's just too hard to actually put your shoulders into it if you don't actually care. So what I would say is I'm lucky enough to work in a department at Wisconsin where pure and applied, we don't have separate departments of pure and applied math. We have like one big department. We're all mathematicians. That's certainly how I see it. I see it as a unified subject where I look at somebody who's a very applied mathematician, and it's very clear to me that they're doing the same thing that I do, maybe with slightly different purposes and in a slightly different area, but it feels the same to me. And so I would say any kind of value judgment I think is inappropriate. I don't think it's appropriate to slag on number theorists like me, I don't think we should have to sort of pretend that we're doing it because, maybe factoring primes is important for credit cards. Like, no, we don't care. Come on. Of course we don't actually care. We care about number theory because we care about number theory. But I also have no patience for like a pure mathematician thing. Like our stuff is like the real stuff, the pure stuff that's like not contaminated and sullied by the real world. I think it's all the real stuff.
Okay, so we almost finished, but let's tell us about the new book, because I know that it should be in Ukrainian like in the future, but I don't know like when exactly.
Yeah, it's
about
going
the
to come
shape.
out with the same publishing house, Nash Format. You did a great job with the first book. So I don't know if it's been translated yet, but I know that they've purchased the rights and will be translating it. So the new book is about geometry. It's a little bit more focused, except that geometry is such a broad subject that in the end, it's not that focused. I mean, I write about all kinds of stuff from the kind of, the way this kind of surprisingly geometric issues of like how we form legislatures in democratic countries to questions about the underpinnings of machine learning, which I know we talked a lot about today, but the actual guts of a machine learning system, a so-called neural network, are very geometric in nature. And I think sometimes we let it seem like it's magic, and it's not so magical. It's actually like pretty straightforward to sort of explain what the basic principles are. And then just, well, to be honest, because I was writing in 2020, I wrote a lot about the geometry of disease spread too, which a good example of something I didn't tell the publisher I was going to write about. But then, of course, like a lot of people, I was thinking about that a lot in 2020. So I wrote about that too. So so yeah, in English, it's called Shape. Okay, so how would you translate that in Ukrainian? What do you think? Since apparently they didn't do such a good job with the translation. The first title. That work as a
Actually,
Ukrainian?
there are some issues not only with the cover, the name of the book, but inside, as I mentioned, that, for example, you try to tell about that correlation doesn't mean causation, and they translated that like a picture with jelly beans wrongly, like in in causation way. It was so funny because because I know that you like spent a lot of time to like explain that it is important to distinguish these two parts, and then in Ukrainian one you have surprise. But still, I really happy that such kind of book have at least translation in Ukrainian, because you know that I guess like the most of educators, like math teachers in Ukraine, they don't know English and can't read it in English, unfortunately. And of course, it's a huge opportunity to read and see broadly, because your book it's fascinating. I quote it a lot for my students with the conversation, etc., etc., etc. So Shape, okay. It's interesting how to translate it, because you can translate directly, like form some kind of this, or you can create maybe something interesting. It's like with movies, when you see like English one and then Ukrainian translation, it's, oh my God, what is the connection? Oh, my okay. This my colleague in the chat remind me to tell, like, okay, the last story about Ukrainian translation. You had in your book the table with a division of, I don't remember, like 50,000 people in 4 parts, and the translator and you write like handwriting something like 5,000, like 5 is really similar to S, and 000, and they translated it like so in Ukrainian one. And you have like the table not with digits, like not with numbers, but something very
Like it was like,
really.
oh my God.
Yeah, and yeah, it was so funny, because I like read it in Ukrainian and it was like, what is this?
Oh no, this is a problem with me using all these handwritten figures. But I like that. Actually, one of the fun, I love seeing the translations, and of course I don't read the other languages, but I like seeing their translators attempt to imitate my handwriting in all the other different languages,
Yeah, but it was very really
interesting.
interesting.
Okay.
But according to Kahneman, it's useful sometimes do some kind of mistakes, because you need to think deeply, like more deeply in that way, and to check what is the table, what is the content.
I'll make my 5s more
really
pointy next time so they don't look like S's.
Okay. Okay, so I guess we should go to the end of our conversation because we
Well,
have
thanks.
1 hour.
It's been really
Yeah.
great. And I hope everybody watching on YouTube had a good time. I'm glad there were so many questions. That's always very fun for me.
Yeah. Thank you
and-
so much. It was a
Thank you.
great conversation about mathematics.
Have a great evening, everybody.
Yeah, and I'm looking forward to your book in Ukrainian. I promise that my community will read it just immediately.
I'm happy to come back and talk about it.
Oh, okay,
guys are
got you. Okay, so thank you to all our viewers on YouTube.